Hi, everyone, and welcome to today's webinar, Garbage In, Garbage Out, Poorly Curated Data is Killing Your AI Models. We'll just give the rest of the participants 2 minutes to trickle in. In the meantime, strap in or grab a cup of coffee. We have a lot of exciting things to show you today. And for the people who just joined now, we'll just give the last participants 1 or 2 minutes to come in, and then we'll get started. Good, we should be ready to go. Hey everyone, and welcome to today's webinar. Today we're going to talk about garbage in and garbage out, how poorly curated data might be killing your AI models. On behalf of Anchor, I'd like to say thank you to all of you for taking the time to join us here today as we discuss and dissect some of the latest challenges faced by AI teams when building models in computer vision. By way of introduction, my name is Nikolai, and I'm the product manager here at Anchor, and I'm joined here today by my colleague Alex, who's our ML solutions lead. We have a packed agenda for us today. We're going to start by making sure we're all on the same page about data quality and why it matters. There's a lot of terminology going around in the industry, so stick with us. We'll explain them as we go. Then we'll briefly share a consolidated view on some of the challenges we see AI teams are facing within data cleaning and curation. We'll use that as a springboard into some of the most exciting techniques available now and coming soon for creating high quality data. And afterwards, we'll dive into a 15-20 minute live demo of some of these technologies with Alex. If there's time left at the end, we'll try to address some of the questions that the audience sent ahead of time. And before we get going, please let me start by thanking all of you for joining us here today and sharing many thoughtful questions ahead of time. Sounds like everyone is very interested in this space, and we're looking forward to the discussion today. Let's get started. So once again, we're from Anchor. Anchor is a data development platform specialized in AI. We help sophisticated and global teams manage their entire AI data lifecycle, from data management and cleaning to automating and evaluating the labels, and lastly, evaluating the models, finding edge cases, and debugging. If you see or hear anything interesting today, please feel free to reach out to Alex or I after this call. We're on LinkedIn, GitHub, or wherever. We talk data-centric AI all day. Would love to chat with you about any problems you might face or questions you might have. So taking a step back, machine learning and AI has been on a wild ride. And I think many of us here would feel pretty honored and excited to take part of this journey. The academic community is releasing new research every week, and we don't go a month without a new foundation model, be it like a large language model or a large vision model. For example, the Gemini 2 from Google released just a few hours ago. At the same time, consumer applications like ChatGPT and Tesla Autopilot are seeing mainstream adoption, while this year's CES gave us a sneak peek at the sheer number of AI-assisted consumer products that's about to hit the market. For us here at Anchor, it seems like the future of AI is now. But with more advanced technology, customer requirements, and problems to solve, the need for smarter techniques to handle data has never been more urgent. What do you say, Alex, about all of this hype?
Thanks, Nico. So one thing that we like to do here at Encore is take a look at what sort of outsiders or experts kind of see where they see the field, and they see the field of computer vision. A classic kind of Gartner hype cycle diagram. You can see computer vision here, and this was published just last week. Computer vision on the kind of extreme right, so on the plateau of productivity. I think if you took this at face value, right, maybe you're thinking of what next project to kick off in your organization, maybe an acquisition of some technology, purchasing some software, investing in a company, you might think computer vision is mature. What I see out there is what is possible, right? There's nothing more to come from computer vision that's going to be completely transformational, right? Because everything is productive. I think if we look into both the real world and the software world, that's very much not true, right? I mean, how many vision systems do we interact with naturally in the wild? Not that many. Maybe some self-driving cars in San Francisco, a few CCTV systems, nothing, immediately, sort of game changing for the very long term, but also in terms of software, right? So image categorization, very useful on your phone. You can get nice memories, but are we accurately detecting cancer in clinical environments in the fully automated way and spreading that capability and knowledge around the world? I don't think that's currently the case. We don't think that's currently the case. And we would actually kind of bring computer vision back to the trough of disillusionment, because I think saying that we're all the way there with computer vision is actually kind of a sort of, that would be a sorry state of affairs if that was the end. The position of computer vision depends on how powerful we think it can be. There was some hype, in the last kind of 6-9 months around kind of pure LLM work. And then a few months ago, we kind of came back to multimodal, right? All the big players releasing vision language models, which are fundamentally, vision based. Computer vision is a huge part of those models. And so how good do we think it can be? We think it can be a lot better. And there's a lot of change and latent kind of productivity and capabilities in computer vision.
But that seemed, Alex, there's a lot of terms here we need to learn a bit more about. You see here, neurosymbolic AI, AI trism. It's going to be interesting as we move forward, indeed. But thank you. And while we're talking about the future of AI, let's just quickly dissect the three main pillars that go into creating an AI model. On a high level, these are models, compute, and data. And models and compute has been rapidly evolving, with big tech incumbents and well-funded startups leading the charge. Today, as you know, most state-of-the-art models are available open source over a few lines of code via Hugging Face on OpenAI API. And similarly, on the compute side, it's quickly becoming a commodity, though an expensive commodity. And this commodity is available in the cloud via all of the large cloud providers, naturally supplied by NVIDIA, that has like a huge market monopoly on the AI chips today. So that leaves data. And data is the main lever for AI teams and companies wanting to build AI models today to build a truly competitive edge in their products. Everyone will use the same models or some variation of the same state-of-the-art model, and it will tap into the same type of compute resources. But all of you will have your own proprietary data to train and fine-tune your models on. With this development, we've also seen a shift in how folks think about AI. So from this traditional AI that was built from scratch, unimodal and model-centric, and only for technical users. Today we see a more modern AI, which is building on foundations, as in these foundation models and large trained models. It's multimodal, and it's inherently data-centric. In the last two webinars, we covered these first two blocks. So we had foundation models where Justin and Frederick, they discussed LLMs and VLMs. And then last month, Alex and I, we discussed multimodal models and their potential to act as a specialized agent with no fine-tuning or training. Both of these you can, of course, check out on our website if you want to rewatch and relearn some of these things. Today, we'll mainly be focused on this data-centric piece. But before we do that, Alex, we've all heard this term before. Bad data equals bad models. Can you please elaborate a bit more on this today, but give us some detail, not just a high-level description?
Cool. So I think the bad data, bad model, you've heard it a few times. I think to your point earlier around those foundational pillars of AI, right? So compute and models, and then also data. Model architectures have become a lot more standardized and clear for specific problems. There's still a lot of research going on in those, but for most kind of enterprise problems, these are relatively standardized. And depending on what we feed into, let's say, a fine-tuning process, which is kind of the most common adoption of AI in an organization, you're not going to go and train a foundation model from scratch. It costs you millions of dollars. You're going to show it some specific data and fine-tune it for your application. If you just took the entire contents of your data lake, your S3 bucket, tried to put those into a fine-tuning process, A, you wouldn't have a huge amount of kind of context on that data, and B, that data might be polluted, it might be low quality, and your model will end up learning potentially undesirable behaviors, right? Even if that's just pure text. We saw, for example, with Google's models, I think there's some training on Reddit data that led to some unpleasant kind of behavior when doing question answering. That's not something obviously we want to avoid, right, in that curation process. And even people developing the biggest models suffer from this. So it's something that we definitely need to be on the lookout for. And we'll go into a bit more detail later around forming the right data structures to then actually enrich the high quality data.
Of that said, Alex, does it mean that great data equals great models?
Yes, so that's the next step. I think we sometimes often focus too much on the cleaning bit, which is the bad data, bad model, which is still really important as a first step. But actually, it's a positive piece, which is curation, right? And that's the great data, great model side of things, where we find the most impactful, relevant data to fine tune a state of the art foundation model on for a specific domain. That data is probably not publicly available. But if in our own data lake, we need to make sure we select the right things. And secondly, with great data, we're not just talking about great data assets, right? So great videos or great images or other kinds of modalities like medical scans or point cloud, those kinds of things. It's also great data structures. Like we've now moved to a state where we're much closer to traditional development. Right? If you want to start a website, you think about the access patterns, you think about what you're trying to do, and you think about the data modeling and the data structures. And when I say data, I mean the metadata, right? So the labels, the things that are associated with the raw assets. So great data and great data structures equals great models. And also that's caveated with not necessarily big data, because these foundation models have already seen a lot of big data. And so it doesn't take necessarily that larger volume of data to shift them to where we need them to be for our application. Great. This sort of reinforces some of the previous points. So the architectures have now become quite standardized and mostly open, at least on the state of the art, right? And for most problems that we would look to build our own models, at least on a commercial level, rather than a purely academic level. Architecture is open source. Often, we get the training weights, also publicly available, friendly. Academic sources give us different model sizes, which are really useful. So we can choose depending on what our inference environment will be, right? We can select the right kind of baseline and the volume of our fine tuning as well. In terms of, doing something that's going to be a specific field, an example from one of these models, for example, would be, let's say SIG anything, right? Great model trained on a lot of kind of, internet data, common data. If you have a manufacturing line that's manufacturing a specific kind of types of bolts that are used in medical equipment in a specific geography, it's very unlikely that these will be segmented to the same degree of quality as the types of images that have been seen and are common on the internet, right, for training these huge models. And so a fine-tuning process would be really valuable there. Similarly for the large language models as well. I think we'll dig into Lava, for example, a little bit later on in the talk.
For those of you that just joined now, of course, if you have any questions to Alex or me as we go here, you're more than welcome to just throw them in the Q&A. Then we'll either take them as we go or we'll take them at the end of today's webinar. Super. Maybe one more example, Alex, here about this small data but high quality, just so everybody understands it completely.
Sure. So this is a kind of screen grab from a vehicle driving around, right? And you might look at this and think, this is great. This is super high quality data, right? I've spent lots of time building this. It's really complex. I can do something very advanced with this. And yes, of course, segmenting can be complex, but now we have a lot of models to help us, like SAM, etc. So here we've got purely geometric labels as well. This is just an image, right? It's not a video, so we're not even talking about like temporal stability of the geometric labels or even any kinds of hierarchies and maybe like causal metadata that we might capture as well in the labeling process, just a single frame. But if we move into the next slide here, you can see that there's a whole lot more context that we might need to add, right? So model that's going to be driving around, it's going to need a lot more context to make consistent, reliable decisions and explain its actions, right? And you can see here on the right, we have an example of a structure, right, that we might add for a labeled pedestrian. So not just the pixels that represent the pedestrian, but the state of the pedestrian, right? Is it you walking or running? Subjective things like eye contact, and was it partial or accidental, right? And these things become quite difficult actually to label, right? And we can use self-supervised approaches and don't need to label everything, but these kinds of things typically will need some human involvement to move the data generation process basically up the value chain, right? We're not interested in drawing bounding boxes around cats, but we need to analyze broader context about the data that's going to be processed. So having this data be small but also mighty is really critical so that we can correctly allocate resources in these domain-specific applications.
I know you also brought an example here from the real world. Can you talk a bit about what happened at Wave here?
Yes, so we were at CVPR last week. There was a great kind of workshop for the workshop on VLA-DRs, and Wave was presenting. They also had a booth where they were showing some of their latest work. I think this is really interesting, right? It's that sort of multimodal approach where previously at previous conferences we'd see images like you'd see on the Tesla self-driving, right? Just kind of things being detected. That's great. But here we're kind of seeing a much more complex thing, right? We're seeing a sort of chatbot associated with the self-driving model. We're saying like, why are you turning right? Like, oh, there's a pedestrian there. I'm going to slow down. I'm going to avoid the pedestrian. The pedestrian looks like he's going to pull out, right? So it's all explainable and allows us to build much higher quality models. So you can challenge and query these driving models. And there's a clear link between what we showed in the previous slide, so a complex labeling taxonomy, and these kinds of capabilities.
Gotcha. But Alex, let's just take one step back to these foundation models you talked about that are trained on vast amounts of data. Why do they actually need this special work and fine tuning to be able to run really well in these certain domains? And like we can all see ChatGPT is powerful, but how come that we need to fine tune it for these particular environments?
Sure. Yeah, so it's all around the data that they've seen. And so these models are great. They've learned a lot of general things, right, about the world. So they're still very useful, right? They learn how to what an object is. They learn a bunch of things, right? But they are not going to have kind of domain specific information, right? And they're not going to have been tuned for specific use cases. So they're a great starting point because they have a good general understanding like of the world, right, and what they're seeing. It costs a lot of money to train, so we don't want to start that process again. But in this medical example, which is a very concrete one, most models haven't seen specialized medical imagery or medical captioning. And it's a similar example, I think, this fine tuning process of medical students, right? They know a lot of general things about the world, but they haven't yet studied medicine, so they haven't fine tuned their brains. And that's basically what we're doing in this example. So Lava, open source model by Meta, so it's one of these vision language models. There's a version called Lava Med, and this is really interesting because instead of using kind of 2,000, A100 GPUs and spending millions of dollars to generate the initial foundation model, you can see they used 8 GPUs over kind of less than a day, right? So computationally, a lot less expensive. And then in terms of the data that was shown to the model, you can see two stages. One thing which is really interesting to point out is that for the first stage, the medical concept alignment, they actually took a data set that had 15 million assets, so PMC 15M, but they only used 600,000 samples in there. And so they talked about curation of that data set because they only wanted to show high quality, diverse, balanced data to the model rather than just throw everything in because it could be redundant. It could also, the learning process might not be focused on the objectives that we want to achieve. The last thing to note here is that it's not just about kind of human data, it's also about kind of human machine collaboration, right? So the second stage around prompt engineering and using GPT-4 to basically generate a lot of data, like conversational data that we use for that instruction tuning, but with humans being able to focus their attention on the hardest cases, right? Not on just generating baseline data. I think the result is probably the kind of most interesting thing to look at here. And so you can see what we're looking at here is at the top, you can see there's a kind of an X-ray, and then we've got two models that we use. There's Lava at the bottom, which is the original model, and then Lava Med, which was fine-tuned. And we're asking Lava what's being shown in this image. And it's saying that it's likely a medical illustration. That's the red line that's underlined at the bottom. I think that's something I could probably have told you. I'm not a doctor, but I think that's probably a medical illustration. So it's not very useful, at least in a clinical context. Whereas the top one there is talking about the green line. You can see we've got bilateral patchy infiltrates and talking about lung opacity and these sorts of things. And so that's clearly a much more appropriate model. Now, this isn't quite ready to be used in medical environments yet. There's still it's an academic project, but we can see how this brings us towards the path of fully AI doctors that we can deploy across the world. We can deploy in the field, these kinds of things, speeding up like real life impacts, which I think is really exciting.
Now we saw here that the Lava Med team, they reduced their data set from 15 million to 600K. And with all this laid out, let's just dive into some of the data creation trends and data quality trends that we see. and talk about some of the pain points that we've uncovered working with different AI teams over the past few years and what they were facing on their journey. But first, here quickly to put things into perspective. Here we see what a computer vision data pipeline used to look like. So this will be years ago. You'd have a data collection, storage, annotation, model training, evaluation, and lastly, deployment. Back then, computer vision projects were often quite niche. They were undertaken by a single data scientist, researcher, or ML engineer, or maybe a small team, depending on the size of the company. Here, the small team of data scientists was responsible for all steps in this flow. In these days, requirements were low, data volumes were low, and model capabilities were often quite limited. However, as these vision projects, they increased in scope and AI rose in popularity, multiple stakeholders joined in. So now it's not only data science teams, but it's also data ops, the newly invented ML ops, and often multiple layers of management that gets involved. So this new complexity combined with increases in ambitions and project scope brought with it the need for a lot of new tools and processes that we can see here on the screen today. And we'll be focusing on these first two. So how to conduct data cleaning and curation to essentially manage, structure, and reduce the size of your data sets, similar to the LavaMed team. Of course, promise we'll get to the rest of the stack at future webinars. Before we go, let's just get some quick definitions in place. When we talk about cleaning, we're referring to identifying and correcting errors and inconsistencies in your data. And we'll talk about curation, we're referring to the organization and management of data to prepare it for labeling and model training. So cleaning is all about removing the bad data, and curation is all about selecting the great data or the right data. Next, we can talk about what we typically see folks they're doing. So when we've been talking to teams, there's a few methods that kept coming up here. The first one, and probably the most atrocious, is manual inspection. So here, people, they would manually inspect hundreds of thousands of images and frames, where the team, they would sit and simply scroll through hundreds of videos at the same time. This they would do to select the best images or clips to find any clear outliers, any clear issues. Of course, this makes it very hard to spot outliers, duplicates, or errors. Second, after this are like one-off scripts in Jupyter Notebook or local Python environment, where they would analyze the distribution of the data, different classes, conduct various analyses on the data properties. The downside here was that it's hard to reproduce a lot of these things, and often you had to fetch the data to disk. So of course, it's naturally not that scalable. Third part were some immature open source toolkits or home-built Streamlit apps, which though very helpful for POCs, not very sufficient for scale, more advanced processes, keeping track of the activity logs and so on, and of course, automation. So if we distill down some of the common problems that then surfaced when you use these unstructured processes, for cleaning, it's mainly a lot of duplicate samples that can skew your training data and impact the training of your models, potentially leading to overfitting. There's similarly corrupt data, which can have a big impact on the model downstream. Noise in the data, which can obscure different patterns. And then lastly, data outliers, which in some cases would represent valuable edge cases, but in a lot of other cases would be misleading anomalies or out of distribution data. For creation mistakes, we often see teams are using a completely random selection method to select their data for labeling. So they're not using any acquisition functions, any model in the loop, or anything like that. Moreover, a lot of these teams, they rarely conducted any pre-labeling of the data. It's a process which, if done right, can save 20, 30, 50% of the labeling time. And then lastly, once data has been labeled, rarely were people passing it through a validation pipeline. This is a very important step because if you don't have a proper label review flow set up, you can end up with missing labels that can lead to gaps in your model fitting the data and learning the underlying problem of your use case. And it can also lead to inconsistent or wrong labels. So if you have wrong labels, they'll lead to unreliable models that would often get different classes confused. Ultimately, all of these problems, they lead down to outcomes that impact our business goals and our business outcomes. First, there's naturally delayed time to market. If you have to label more data, if you have to retrain your model over and over again, that'll slow you down. Secondly, is the increased annotation cost from labeling more data and increased ML ops cost from setting all of this up. And lastly, this is the worst one, of course, poor model quality. If you don't have the right data, you're not going to get the best model. All of these factors are luckily affected by this preparation phase, so the phase that's conducted when you do cleaning or curation. To give a concrete example of one of the partners that we work with that has embraced this new cleaning and creation domain or methods, I'd highly recommend to check out the case study with automotives. So the automotive team, they first cleaned all of the data, while they curated it prior to labeling. But they measured the model performance at each stage to show how the model was reacting at different stages. This led to a 35% smaller training data set and increased the MAP score by over 20% on a validation set. More specifically, they found that the model performance degraded due to a lot of corrupt data in their set, and they uncovered that more than 5% contained duplicates, corrupt images, and irrelevant data points. After this cleaning, they were still left with a vast amount of footage and had no real way to prioritize which footage to label. So they used a diversity acquisition function to curate the remaining clean data and ultimately saving, I think it was up to like 33% of the labeling budget going forward, which is pretty cool. And it's a pretty critical component as they now scale out their labeling and model efforts. So with this said, Alex, how can we distill these learnings together into something more actionable and repeatable?
Yes, thanks, Nico. So as you mentioned, we provide many tools here here at Encore to build out that pipeline. Now here it's shown in a sort of linear kind of left to right flow because of screen space. But we typically see all these stages as cycles, right, within the process. You can see from left to right, we kind of have the different teams getting involved at different stages, right? So data ops, they tend to be responsible for the data collection. They want to do the cleaning kind of piece. We then start to involve the ML team, the curation piece and the enrichment. So they start to have an idea of like what kind of models they're trying to train, what sort of data would be relevant, etc., and what additional context they need on those assets. We then start to involve the annotation team, so subject matter experts, right, which will be involved in that process, especially for advanced use cases to enrich the data, and then back to the ML team to potentially fix any errors in there. And then as those models get trained, right, we can start to build that virtuous cycle to get to a desired level of model performance with the least amount of data and labeling effort. Today, we're going to focus just on the first two stages. So looking at how we can kind of clean our data sets and how we can also curate them so to find kind of interesting and useful examples. The kind of two concepts that we just want to introduce before we jump into the demo is first the concept of quality metrics. So these are going to be kind of derived quantities on the data, which are going to be useful for searching and sorting, right? So things like, let's find underexposed images or blurry assets, or let's use, something like the auto duplicate checker to find problematic parts of our data set. The next one that's useful to understand in this context is embeddings. So essentially, this is being able to take an asset, so an image, for example, generate a vector representation of it. So in this example here, in this diagram, you can see it's just kind of lots of points. We'll be looking at a 2D plot, so basically a 2D representation of what that image is. So images close together will be similar, far apart will be different, but we'll just remember as well that these embeddings are not just 2D. So that's what allows us to do the similarity search. We actually are able to calculate on the full embedded representation of the image. So when we start to see plots with lots of dots on them, that's what we're looking at.
Good. Great. Let's dive into it. I'll hand over the screen now to Alex. Who'll take us through like a step-by-step guide on how to get started. Then we'll show some examples of data cleaning and creation on a bunch of different open source data. And lastly, we'll discuss some automation potential before we return for a Q&A. So I'll stop sharing on my end now, Alex.
Great. Thank you, Nico. Let me give the sharing. Can you now see my screen?
Yes, I can see your screen.
So we have a few data sets that we're going to get through today and just show you kind of different types of curation and cleaning workflows. We'll cycle through different use cases. So we'll start off with a medical one, then look at sort of open source art data set, an e-commerce example, and a few others. So it'll be interesting to see that diversity. So here we have some sort of panoramic dental scans that have been taken. And we're thinking, we're building a model, let's say, that's going to be used in some clinical environment, so maybe on device, or maybe it's going to be something that's going to, be some sort of assistant tool, right, for dentists. Now, we have this initial sort of gallery view, right, which allows us to look at our data, get a bit of a feel for what's going on. But this is typically not going to be really scalable, right? And it still beats just downloading things out of your S3 bucket, which I think Nico talked about, and is not really definitely not a scalable flow. But it's still not, not ideal here to start filtering our data in bulk. So what we can do as a first step, just to get a sense for what's going on, is to go look at that embeddings view. This is a reasonably small data set. It's a very specialized one, and we'll look at some larger ones a little bit later. But you can see here we have these dots that represent data. So as we hover over them, we can see kind of what they contain. So we can see what these different clusters and these kind of similar images are. Now this gives us some intuition for what's going on, but it's also useful to overlay some of those other metrics. So I could say, for example, here you can see we've got brightness, right? So we have some bright and dark images mixed here. Here we have mostly a cluster of kind of these bright images. We can also look at other kinds of metrics. So diversity, for example, which is going to show us kind of in these clusters what might be of interest to us. So I can draw a bounding box around, let's say, this top corner, because I noticed there are some green ones, which have a high diversity. It might be a little bit less obvious to you, the screen share, but I'm going to hit the View and Explorer button, and that'll slim down our selection to what was inside that area. You can see these are quite interesting. We have some with totally missing teeth. You could think maybe there were errors, but I think these are actually legitimate scans, right? Where we just have situations where people have missing quite a few teeth, and this is quite interesting because we've kind of narrowed down into an area that might be something that's underrepresented, right? So these are quite unique images within our data set. These sort of mostly empty images. So this might be the stage where we want to send them to some human experts to give us more context on what's going on. And if you think about medical kind of imaging and medical AI, the type of metadata being generated is going to be expensive and complex, right? So if I say I'm going to tag all of these as being sort of like empty or sort of low tooth count images, if I tag these as being that specific case, and I say, I'm going to go and take those tagged images. As you can see here, they all have this little low tooth count tag. I'm going to take that grouping of images. So you can see here, this essentially represents those 10 images assets that we've selected, right? So we call this a collection, kind of a grouping of images. And I say, I'm going to send this to some clinicians at data. They're going to have to read the patient history. They're going to have to maybe annotate the teeth numbers, the pathologies on the teeth, explain why those pathologies are there. That's going to be pretty expensive, right? It'd be sort of tens or hundreds of dollars per asset. So we really want to be careful in terms of what we're going to send through, because we want to send through relevant data that's going to have kind of the biggest impact on our model, because maybe that's what we wanted to do, or maybe we already had a model and it wasn't doing well on that section of data. So that would be a model evaluation, which is for another talk. But that's all part of that same cycle and that same workflow. Great. We can now move on to a larger data set, which will be really interesting, especially for the kind of cleaning use case. So this is more curation, so saying what's of interest to us, how do we find things that might be particularly relevant. Here we move on to this art data set. So data that could have been, let's say, it could be user-generated content, let's say. And if this was user-generated content, we could expect that the data might not always be of high quality, right? Maybe we don't have the appropriate filters for the data coming in. We've got customers that don't have high-quality devices, whatever that might be. So again, similar approach, right? I mean, we can go into the full embeddings view, right? So we can show all of our embeddings. Here we see a lot more data, right? So a lot more kind of interesting clusters that are being shown. And these are going to have, sort of similar images. You can see these are all portraits in this section. And that'll again allow us to curate if we need to, much like an art curator. If we go back into the grid view, I mentioned around the cleaning, right? I might be interested in bad quality data. Now I could start setting filters. We'll see that in a little bit. But the first kind of natural thing to do would actually just be do a natural language search. So I can just look for corrupt, right? Like, are there any corrupt images? And you can see actually we immediately surface, we identify to be these corrupt assets. Now you can see there's a mix of both very dark, kind of underexposed assets, and also the ones with this sort of green corruption here. Now, what we can do is we can say now that we have this, actually, I'm only interested in these green ones. So I can hit the similarity search button, and that marks this image as a reference, and then tries to find images that are close to it in that embedding space. So we mentioned the embeddings at the start. We looked at the 2D representation. This is doing a search in the full embedding space, so finding close neighbors that have similar kind of corruptions. And you can see there, it's done a really good job of finding out those ones that are kind of closest to the corrupt case. So what I can do here, which is going to be a different approach to the one that we did previously, is I can tag these assets. So I can do the same thing, right? Add them to a collection. I can say, yeah, these are all corrupt images. So I'm going to add them to that sort of green corrupt image collection. So they've again been tagged. But what I might want to go on and do is say, I'm going to ingest more data in the future, right? And I want to guard against this happening. So I still want to be able to tag this. So I'm going to construct a filter, a preset filter that I'll be able to use going forward. So if I go back to my embeddings view and I decide to color things by collection, and I select my green corrupt collection, you can see all of the gray ones, which are not in the collection, and you can see the green ones, which are in the green corrupt collection. And you can see that there are a few that are kind of lying outside here. So that doesn't really give us that much useful information from that embeddings perspective. But then we also have this nice cluster down here. So what we're going to do is we're going to sort of zoom in. So I can go in here and apply the filter. I can go in here. So you can see I filtered down in this particular region. I can even sort of filter down even further if I wanted to, but we'll keep it here for now. I can then go back to my Explorer and see what's present. Now you can see actually that is a cluster of kind of corrupt images, right? It's a mix of the green and the dark corrupt cases. So what I can do now is I can say, okay, I only care about the light ones. So let me just move this around. So I can go ahead and I can select a different kind of filter. So let me just move my zoom share. Seems to be interacting with the browser a little bit. So I can go in, pop in the brightness filter and say I want to only have those higher brightness assets. So they come in. And then maybe I also want to add a greenness filter, right? Because I recognize this is a particular kind of corruption. And so I can go in and I can say I'm going to filter by green value. And let's say only take the ones that have a high value of greenness. You can see that gives us a really nice selection. So I have this more complex filter that I've built, and I can now go ahead and create a preset. So I can say this is going to be my green corruption preset. And now let's say, I ingest some more data and I want to find, that cluster again. I can just load presets and say I want to get my green corruption, and that'll automatically filter things down. And then I can stream those into a collection. So if you think in production, we're going to have a lot of these filters. We have lots of different cases. They could be cleaning, they could be curation cases. Often cleaning is that first stage. And so we can distribute that data into those collections and take some action, right? Maybe we want to exclude it. We're not interested in it. Maybe actually we are interested in it. We want to build a detector for these kinds of corrupt use cases. Great. Nico, anything to add before I move on to the next example?
No, I think it's fine. Maybe one thing to add here, I can see a bunch of questions are trickling in the Q&A. We'll get to all of those afterwards. So when the demo is over, we'll spend the last 15 minutes talking about the different questions. But thank you very much for asking already.
Great. Thanks, Nico. So moving on to another data set, you can see this is a product data set. Now, again, let's say we wanted to find corrupt cases, but we're not quite sure, right? There we kind of stumbled upon that green case, typed in corrupt. That's pretty useful. But let's say it's something that we know is already quite a common type of error that can happen. And so what I can do here is I can say, on the right-hand side, we found some issues in this data set. So this, I didn't have to do this manually. The kind of tool automatically did this for me and flagged these issues. And I can say, okay, I'm going to look at the blurry assets. So just click on that. That'll start to construct my filter for me. So surfacing these blurry images. And this is an e-commerce use case. I moved on from the art curation use case. And then again here, maybe, okay, I'm also interested in these sort of very underexposed images. So also stack a dark preset. So when I get dark, blurry assets, and you can see that filter here in the filter piece will have been already constructed for me, right? So we bring this in. And again, we can take that same approach of setting a preset and using it to stream data in. But the only difference here is we've used kind of a pre-filter that we've combined with another pre-filter to generate our final filter.
Alex, I can see you also have duplicates on the list here. Can you try and show how to find and potentially remove some of the duplicates from your data set?
Yes. So duplicates is a great one as well. People have far more duplicates than typically they think that they have in their data lake. So being able to hit duplicates and immediately surface those is something that's going to be extremely helpful, right? So we can tag all of these and then we can deduplicate them.
Awesome. And then a second thing I think would be worth showing here. Now, this is a fairly large data set, so you're never going to be able to see all of the images. We had this analytics view. We can see different distributions of these metrics. Can you try and show some of that?
Yeah, absolutely. So, filters are great. The embeddings view is also great. And when we go to the embeddings view, we can see single metric values and how they're distributed across the embedding space. So I can say I want to color things right by brightness, for example, and that starts to become pretty useful, or other tags. We have this other view that Nico is drawing attention to, which is the analytics view. And this is where we're going to be able to see essentially the correlation and distribution of these different metrics. So I can say, okay, show me in my data set, what the distribution of, let's say, contrast is going to be. And they'll plot this for me. I can do the same thing with kind of potentially linked values to see how things kind of correlate and get an idea there. Again, I can use the same kind of filtering approach that we saw in the overall Explorer. Things that we won't touch on here are attributes and classes. So as we start to enrich these with labels, we're also able to start to do much more advanced analysis. But that's, again, for a future highly exciting webinar.
Awesome. Do you have other demos projects here for us today?
Yes, we have two more things to show. So the one thing here just to show, which is...
Let's take one more, then we'll go into Q&A afterwards.
Great, we'll do one more. One thing which is really exciting is the sort of multi-object search, which I think is really nice. Something that a lot of our customers have asked for, and we've built, and it's something that's really powerful. So if I scroll through this, you can see I have a cosmetic kind of item here. I can do a similarity search, but to just find similar ones. We've seen that before, nothing sort of wildly new here. But once we've done this once, what we can start to do is we can continue to refine this selection. Right, so I can say I'm interested in the labels, right? I'm interested in the labeling that's written on this asset. So what I can do is I can scroll through, maybe find examples that are also kind of the back of the bottle, right? So these ones here, and I can add them to my current search. And that means that instead of having to draw a box right in the 2D space that we had, which is kind of not as powerful as the full embeddings view, we can actually do this search in the full embeddings representation. So looking at these two assets, and you can see now we're actually seeing kind of a lot of back of the bottle kind of examples. And this could power something where maybe we want to train a model to analyze these bottles and determine whether the contents are safe, right? Because we only want people to sell safe things on our marketplace with proper kind of health warnings. So all these different techniques, again, are stacked, layered, and then end up in presets and then in collections. So a three-step process, kind of finding out filters to find things and stacking different techniques, embeddings, preset filters, similarity search, natural language search, setting those presets and sending all those into structured collections and doing that at large scale. Great. The very last thing, just 1 minute, Nico, I know you want to move on to questions, is just the video view. So we showed this all on images. And I think it's really important to remember that there are other types of assets that are more complex than kind of pure images. And so let's say we had a corpus of videos. I might want to narrow down and find, for example, my videos that are taken in Texas, let's say with GPS recording. And I'll narrow down my selection. And then within these, especially if I have long videos, this is something we see in like surgical video customers, AV customers, I might also want to save the time of my experts by pointing them to specific parts of my video, right? So I might want to say, in this long video, does anything interesting happen? I can see the variation of these metrics through time, right? So we have to remember everything we've seen today. Should images can be easier for a demo, but we scaled, videos, other kinds of modalities, which are also really exciting, and we need the right tools for. So all this kind of goes across the vision stack.
Awesome. Thank you, Alex. I think we have one more minute if you want to show one more, but otherwise I'll head over to the Q&A now. Let me take back the screen. Can you see my screen on your end?
Yes.
Beautiful. So let's jump into a Q&A, and let's start with the questions that have been sent in the chat live, and then we'll jump into the pre-submitted questions. And Alex, I'll read this aloud, then we'll discuss who will take the question, probably answer both of us just to provide full context, and then we'll move on. Of course, if your question has not been fully answered, just feel free to reach out to us afterwards. We're more than happy to chat these through. First question here from CM. How are you determining the duplicates in your view here? Is there any specific algorithm or method? And this is fairly straightforward. So we calculate a derived metric based on the embeddings that ranks how close to each other a given image is in the embedding space. And if this metric is below 0.00001, so essentially if it's the same, then the image is a duplicate. Second question here, can it handle heavy images, so above 10 gigabyte, or 3D images? Which file formats? So today we're working with images, videos, medical images. We are also working with large images, so geospatial images. This could be fairly large, we'll say 8K, 10K, 15K. Of course, there is a limit to when we can calculate embeddings over the images. And all of this is visible in our documentation. In terms of 3D, we're not supporting 3D imagery yet. It's something that we are looking at internally. Next question here from Alberto. Are you using pre-trained models to get a feature-rich vector and then projecting onto 2D using PCA to get the embeddings? So yes, we are using a pre-trained model that's heavily skewed towards both the text component and the visual components. That's why we can use natural language search. And we are projecting onto 2D, but this is using a UMAP reduction, not the PCA. So we played around with the different reduction algorithms and decided that UMAP is the one that gives the best representation. Then we have a question from Percy. So the idea of having quality metrics is essential, and it's good that you can compare between two data sets and assess the quality before and after intervention. I was wondering if there are some standardized metric to quantify the quality of images. If not, what aspects do you usually look at? Seems to me like the demo relies heavily on brightness and contrast. I can start here, Alex, and hand over to you. So the normal thing that we see as the people, they look at various metrics. The main ones are brightness, contrast, sharpness, diversity, and uniqueness. Then they look at the aspect ratios and the areas of the images. And they will sometimes look at the object density of images. There's no such like one metric that can define image quality across all different domains. So we do have custom metrics with our customers where they would give us a particular metric. We would implement it for them and just make it available to them. Anything to add here, Alex?
Yeah, no, I think that's great. I think two things. One is like it's very kind of easy and intuitive to understand image probably brightness, contrast, these kinds of things. We also have that whole category of like sampling functions, so things like diversity, uniqueness, which are really powerful. These embeddings-based metrics, which are also extremely powerful. And the third category, which we touched on at the end, is the metadata piece. So if you have kind of associated metadata, device information, things like that, you can also search by those. And we're also now able to, a lot of customers pulling in LLM generated metadata that they can then search by, which is really useful.
Yeah. And we have here from Muas. How long does it take this platform to read and analyze my data set of pictures and videos approximately? This depends on two factors. So one is the image resolution and size, or video resolution and size. And the second one is the volume. So let's say you come with 1 million images of a 1080 resolution. That normally take 1 to 2 to 3 hours to do the full calculation. So giving you embeddings, derived metrics, and quality metrics. But of course, your data and your labels and some of the simple metrics will be available within 10, 15 minutes. For 10,000 or 100,000, this would be like half an hour, 45 minutes.
The only thing to add there is, that initial import can take some time, but then often these data will then grow by some delta, right? And we then don't need to recompute everything. So it's a lot quicker once you've gone through that initial setup time.
The next question here is from Suraj Kumar. Is it possible to segregate the images and their annotations into different versions of the dataset with only this image? So yes, you can have multiple projects. So what Alex showed before was multiple projects. And you can have the same data set with a different label set in each project. So essentially versioning your labels and being able to compare them side by side in two different projects. And Anonymous asked if there will be a future webinar on the same subject, but with text data sets instead. That's a great idea. We could look at doing something with PDFs or text, Alex. I think we'll chat about that after this call and get back to you. And from Taishu Park, UMAP sometimes requires parameter tuning for proper visualization. Do you provide a kind of auto tune for the parts or do you allow manual setup? So Tashu, today we don't allow manual setup. We've played around with different tuning ourselves, so it's now auto tuned to a specific part. And we could look at it in the future to provide our customers and partners to tune themselves, but it's not something that's coming up in like any time soon right now. But if it's something interesting, please do reach out and we can discuss your use case specifically. That was the pre-shared questions. There's one more here, also from Tashu. For embedding analysis, can I pick a specific embedder? So empirically, the embedding quality heavily depends on the type of embedder. That's correct. We support custom embeddings. So if you have your own embeddings model, you can calculate your embeddings on your end and then import the embeddings into our platform, and we can visualize it for you. So what we use is, of course, a more generalized model that applies across multiple domains. But we are experimenting a lot internally with fine-tuned embeddings, and we do allow our customers to import their own embeddings. Actually, I can quickly give you an example here. There's a little GIF of clip embeddings versus some anchored fine-tuned ones that we did the other day. So this shows you just how much difference there is in your embedding space from this clip version to the left. So the colors represents the different classes. And then after fine-tuning on a few thousand samples here to your right, we can see that the classes are way better clustered in these different areas. Gotcha. Then on to the questions that came in advance. How should companies interpret unacceptable levels of risk? Alex, maybe you want to take this one and give us some input here.
Sure. I mean, it depends on the industry, right? It's a pretty bad answer, but it depends on the company and the industry. An unacceptable level of risk, right? If you're a consumer application and you're very worried about image, etc., that could be just something not going super well. Like maybe just a basic mistake, a misclassification could still be pretty relevant, right? If you have objectionable content detection, those kinds of things, that could be pretty risky, right? An unacceptable level of risk if that goes through your models. And then all the way through to these more advanced, like medical, aerospace, manufacturing, geospatial, sort of satellite imagery applications, where like military applications, where the unacceptable level of risk is basically any kind of error, right? And that's often actually associated with confidence, right, and explainability. So you're gonna make errors, but then can you try and find them? Do you know what's sure, what's not sure, and do you know why those errors are happening?
Thank you, Alex. Next up here, how does the industry tackle conflicting image annotations by different annotators? Like one person may think the feature counts as a magnetic cell, and others may think it isn't. It's a great question. It's a very common problem, actually, especially within the medical AI industry, where tasks often requires a lot of attention to detail and annotators with domain expertise. So what we normally see our partners and customers are doing is that they're using a consensus-based approach. So this means that they're comparing multiple annotators against each other on the same assets, so the same scans, and then they're visualizing them in the editor on top of each other and selecting a winner. So either manually selecting the winner or they're using their own consensus algorithm that they can plug into our platform. So we do have like a full consensus module for these type of workflows, and it's very popular. Is it worth it to fine-tune embeddings for cleaning and creation? This is very similar to the question that came in from Tai Su before. I think I'll go back here and just talk a bit about fine-tuning and curation. So as Alex showed before, the embeddings view is very often used in the curation process and in the cleaning process. And if the representation of your images gets more refined and more fine-tuned, naturally the outcome of your work will, of course, give you better data, greater data, and cleaner data. So this is just a 2D representation, but naturally the embeddings come in, I think these that we used here for clip is 512 dimensions. So you can imagine that the 512 dimensions are all better represented across your images that you have. So I'll definitely say it is worth it. Look at the compute cost it takes for you to compute your own embeddings. Look at what different types of embedding models there are out there. We've seen a lot of clients, they're using Hugging Face models. So they're just using a fine-tuned version of Clip, for example, to then calculate the embeddings and import them into our platform visualization. What are some new tools and techniques that are upcoming on your roadmap? Good question. I think I can lift the wheel here on two things. So we're looking at automated failure clustering right now. So bringing in your model predictions and automatically clustering which images that your model is failing on. So that might be, as you see here on our right, we have a 30% lower precision when model confidence is low and the relative area is low. Or might be lower recall when redness is lower than 0.75 and border proximity is higher than 0.87, class is person. And then maybe that the average true positive rate is lower when aspect ratio is not a given size and the annotator is a specific person. So using different, I have a linear probe or k-mean to figure out what are the different clusters that we can create based on your data and based on your model. Another one is what we call smart sampling. So allowing you to bring even more active learning functions into the platform. Today we support uniqueness and diversity and your own custom, but we want to make some available within the platform for you already. So that means these confidence acquisition, margin, variance, and entropy. And then the last question, what ways can I filter my data set? Could I use a form of natural language search? I think we covered that in the demo before. So of course you can filter based on all of the metrics, filter based on your collections, who annotated your data, which classes, which integration is coming from which data set. You can also filter with the embeddings, and as Alex showed, with the natural language search. Super. With that said, that is all for today. Thank you very much for staying with us all the way to the end and listening in. It's been a pleasure hosting all of you today and hope to see you in the next webinar. Have a good day.